All right, let's dive deep inside your computer. We're going to look at the microscopic highways that make everything possible, and the incredibly clever tricks engineers use to prevent digital traffic jams. You know, it's something we totally take for granted. But seriously, think about it. Billions of calculations, every single second. How is that even possible? Well, the secret isn't one impossibly fast worker, it's an impossibly efficient factory. So, right at the heart of your computer, the CPU, it doesn't just do one thing at a time. Nope. It works like this super sophisticated assembly line, where every single instruction is like a product being built in stages. And this whole magic trick is called pipelining. See, an instruction isn't just one single event. It's a series of smaller steps. And by breaking it down like this, the processor can start working on the next instruction before the first one is even finished. It's all about squeezing every last drop of performance out of every single clock cycle. Okay, so take a look at this. Time is flowing from left to right, measured in these things called clock cycles. Now notice how you've got multiple instructions, like sub for subtraction or and for a logic operation. They're all in different stages of being finished at the exact same time. One is just being fetched while another is already executing. This overlap, right there, that's the key to the insane speed of modern processors.
Okay, but this beautiful, super efficient system, it has one major flaw. What happens when one part of the assembly line needs a piece that a previous part hasn't finished making yet?
In the world of computer architecture, we call this a data hazard. It's basically a dependency problem. Let's say instruction B needs the answer from instruction A, but instruction A is still chugging along the pipeline. If we're not careful, instruction B is going to grab old, totally wrong data, and our whole calculation goes right out the window. And right here is the problem in action. The AND instruction needs a value that's supposed to be in a temporary spot, a register called X2. But the SEP instruction, which is supposed to put the right value there, isn't going to be done until clock cycle 5. The problem? The AND instruction needs it way back in clock cycle 4. It's asking for a result that literally doesn't exist yet, and the entire assembly line is about to grind to a halt. So what's the fix? Do you just slam on the brakes and stop the entire assembly line every time this happens? I mean, you could, but that would be crazy inefficient. Instead, engineers came up with a much, much more elegant solution. Instead of making that second instruction wait around for the result to go all the way to the end of the line, what if we could just, I don't know, intercept it mid-process and send it directly where it needs to go next? What if we could build a secret shortcut? So on the left, you've got this simple setup. It works, but it's prone to those traffic jams. Now look to the right. This is the upgrade. See all those new wires and logic gates, the parts highlighted in blue? That is actual physical hardware that's been added for one reason, to create these shortcuts. And this is what we call data forwarding. The second a result gets calculated in one stage, a special forwarding unit snatches it and sends it directly back to the input of an earlier stage for the next instruction. It's like having an express lane on our digital highway. We completely bypass the traffic jam without ever even slowing down. Now, this forwarding thing, it is brilliant. It handles the vast majority of these data hazards beautifully. But there's a catch. There's one specific case where even this super clever shortcut just isn't fast enough. Think about it for a second. Forwarding works because the data we need, well, it might not be finished, but at least it's somewhere inside the pipeline. We can grab it and send it back. And here is the absolute key. Getting data from the main computer memory is way, way slower than doing stuff inside the CPU. So when an instruction has to load data from memory, there's a built-in delay. The data isn't even in the pipeline yet, so there's literally nothing to forward. And boom, here it is. This is a classic load-use hazard. That load instruction is fetching a value from memory. The AND instruction that comes right after it desperately needs that value. But by the time the AND instruction is ready for it, the load instruction is still in the memory access stage. The data just isn't there. Our fancy shortcut has nowhere to go. Okay, so if our slick, elegant solution won't work, we have to fall back on something a little more brute force. It's not as pretty, but it is guaranteed to work and, most importantly, prevent errors. That's right. If the processor's hazard detection unit sees one of these load-use hazards coming, it intentionally stalls the entire pipeline. It forces a one-cycle delay just to give that slow memory operation time to catch up. See that? Right there in the pipeline, for the AND instruction, it's labeled bubble. That's the stall. The processor literally injects a no-operation command, basically telling that part of the pipeline, hey you, Do nothing for one cycle. And that one cycle pause is just enough time for the data to finally arrive from memory and be ready to go. And how it actually works is pretty clever. A special detection unit basically turns the stalled instruction into a do-nothing command. That's our bubble. At the exact same time, it tells the part of the processor that fetches new instructions to just take a break. This freezes the front of the line, which prevents a huge pileup while the bubble passes through and the data we need finally arrives. So let's put these two side by side. We've got two tools in our toolbox. Forwarding is our go-to, our number one choice. It's an elegant, zero-cost shortcut for when the data is already inside the processor. And then stalling is our safety net, a brute force pause we only use for that slower load from memory case. One is all about cleverness, the other is all about correctness. And here it is, the whole shebang. The forwarding unit is constantly scanning, looking for any opportunity to create those express lanes. At the same time, the hazard detection unit is acting like a traffic cop, specifically on the lookout for those tricky load from memory situations. If it spots one, it slams on the brakes and tells the pipeline to stall. It's this perfect partnership of hardware working together to keep things fast, but more importantly, to keep them correct. And this really gets to the heart of it. In processor design, you've got this constant tension between raw speed and guaranteed accuracy. A stall might cost us a single clock cycle, a tiny blip in performance, but that's an infinitely small price to pay to make sure the billions of other calculations are exactly right. So let's do a quick recap. Pipelining is the assembly line that makes processors so fast, but that assembly line can get traffic jams, which we call data hazards. Our main solution is forwarding, which is a really clever shortcut. But when that doesn't work, specifically when we're waiting on slow memory, we have to use our fallback, stalling, which just hits the pause button for a cycle to make sure everything is correct. So we've pretty much cracked the case on data traffic jams. But what happens when an instruction doesn't just need a new piece of data, but tells the entire program to jump to a completely different spot? Now that causes a whole different kind of traffic jam. But that's a story for another time.